My name is Jonathan Pearson. I'm a second year PhD student at the Laboratory for Galaxy Evolution and Spectral Modeling, GALSPEC, at EPFL in Lausanne, Switzerland. And in this talk, I will present some of the work that I've been doing during my PhD. More specifically, I will talk about a new physically motivated subgrid model for supermassive black hole accretion that I've been implementing in the astrophysical code ARIPO. And I should also say that this has been done in collaboration with Michaela Hirschman, my supervisor, as well as Robin Tres and Marion Farsi at Galsbeck as well, and then Ralf Klesen in Heidelberg, Germany. Right, so, but before I go into the project itself, I just want to quickly give a short introduction, starting with supermassive black hole growth. So as we all know, observations have shown us that there are strong scaling relations between the mass of supermassive black holes in galaxy centers and some properties of their host galaxies, such as the stellar mass of the bulge. And this seems to hold for all different kinds of galaxies. And overall, this seems to suggest that there is some sort of co-evolution between supermassive black holes and their host galaxies. And cosmological simulations has proven to be very successful when it comes to studying this co-evolution. However, they've been successful in, for example, recreating both large-scale features and observed scaling relations. However, they struggle to reach consensus at higher redshift and instead predict fundamentally different black hole and AGN populations. And to illustrate this, we have here to the right a figure showing black hole mass offset versus redshift. We can see here that there is a large dispersion towards redshift 6 between different types of cosmological simulations. And this could be due to many reasons, but most likely it has to do with the various often ad hoc subgrid models that they have implemented for example, black hole seeding, accretion, and feedback due to the limited resolution in these type of simulations. And while these cosmological simulations have been around throughout years, other type of simulations more dedicated to black hole accretion have been performed, such as GR-MHD simulations. And these type of simulations has really pushed black hole accretion theory forward. Here we can see a snapshot of one of these simulations. And it is now generally assumed that we have two modes of accretion and feedback. At high accretion rate, we have something called a cold mode, where we have a geometrically thin, optically thick accretion disk, while at lower accretion rates, we instead have a hot mode with a geometrically thick, optically thin, advection-dominated accretion disk. And with these very detailed results of GR-MSD simulations, it is now possible to more accurately model black hole accretion and feedback in intermediate to larger scale simulations by adjusting these detailed results to our subgrid models. And this leads us to the science objective of my work and my PhD, actually, which is to investigate how supermassive black holes grow in mass in a well-resolved ISM, together with the high-fidelity models for ISM physics, star formation, and stellar feedback. And here are some of the key science questions that I want to address. So under what conditions can stellar feedback regulate supermassive black hole growth? Do supermassive black holes achieve Eddington or super Eddington accretion? If so, what are the timescales of this? And then thirdly, to what extent does AGN feedback actually regulate supermassive black hole growth? Is, for example, stellar feedback maybe enough for this? And to approach this, what I've been doing is that I've been implementing, firstly, a new physically motivated subgrid model for accretion in the moving mesh magnetohydrodynamic embodied code ARIPO. And this model follows the high fidelity predictions made by three-dimensional GR-MSD simulations. And Right now, I'm mostly focused on idealized simulations because it's a good starting point to try to bridge the gap between smaller and larger scale simulations. Right, so let's go into the accretion model. So I don't have a lot of time to go into the details, but the main idea is that infalling gas will form an accretion disk at the circularization radius and fuel the black hole on a viscous timescale. So we have our Voronoi mesh, which is the case in Aripo of gas cells. And we have our black hole here represented by an orange dot. And firstly, we estimate the infalling gas accretion rate according to this formula here, where we take into account the mean density and mean mass-weighted radial velocity of gas cells fulfilling a set of accretion criteria. And in order to scheme mass of cells, they have to be within an accretion region defined by this accretion radius. They have to be gravitationally bound and has to have a converging flow. Then we can simply scheme mass of these gas cells according to the infalling gas accretion rate, and we simply just distribute this accretion rate over the gas cells fulfilling the accretion criteria. I've also implemented the option for density smoothing, so you smooth the density of cells that have been accreted from, and this is to avoid sometimes numerical effects. But yeah. Next, we have the subgrid model. So once you have accreted mass from your cells, they are entered into a subgrid model. And in short terms, the model basically consists of 3 mass bins. So you have a gas reservoir where your gas initially ends up. From there, you let it free fall on a free fall timescale down to an accretion disk. And there you switch to a viscous timescale. And that depends on the viscosity parameter alpha, the circularization radius, and the black hole mass. And the circularization radius can be fixed at, for example, 100 times the Schwarzschild radius. However, to better take into account the angular momentum of your infalling gas, I've also implemented the option for a variable circularization radius, such that it depends on the angular momentum of your accreted gas. Right, so let's go into some early results. So mostly I've been performing these smaller scale gas cloud simulations, and this is just to test my accretion model to see how it behaves in a very extreme environment, but still very controlled. And I've been trying different clouds with varying properties, such as the density profile, position, and rotation of the cloud. And even though the simulations are quite simple in their nature, they still include a lot of the ISM physics that we want to include in galaxy scale simulations, such as a chemical network, dust shielding, and H2CO self-shielding, as well as radiative heating and cooling of gas. And then just to illustrate some how the accretion rate evolves. So here we have a uniform collapsing cloud around the black hole. And we show the zinc accretion rate, so the initial one, and then we have the black hole accretion rate for a cloud with and without rotation. And what we can see here is that we first have a steady increase in the black hole accretion rate, as expected, due to the uniform density profile. Then after the collapse, which happens around 0.2 million years, the black hole continues to accrete thanks to the accretion disk, while the zinc accretion rate really drops to 0. However, what we can also see is that there's basically no difference in the black hole accretion rate compared to with the 2 clouds with and without rotation. So this is where the variable circularization radius comes in, and we can see that we get now a longer time delay between the zinc accretion rate and the black hole accretion rate, and there's also now a difference between the 2 clouds with and without rotation. We can also include the 2 modes accretion. So basically where you only update the variable circularization radius above this 0.02 anytime limit, And we can see that we avoid these very low accretion rates at the start, and then it slightly changes the accretion rate at the end as well. Right, so right now I'm in the phase of running more galaxy scale simulations. So, for example, an M51 like galaxy simulation, and this includes all of the ISM physics that I talked about earlier, but also now star formation and stellar feedback. And in terms of resolution, they are this one here is around 1,000 solar masses in gas and star particle resolution. And in terms of physical resolution, it can reach sub-parsec resolution. And this is just early results, but so far the black hole seems to grow very rapidly at start. But we will see later on when we have more snapshots how it evolves. Right, so I'm running out of time, so I will leave you with my conclusion and just highlight some future work. So in the future, I would also like to do simulations of high redshift typical dwarf galaxies to see how they are regulated by stellar feedback. And then also we would like to include feedback, of course, such as radiative feedback, and this will be done together with radiative transfer on the fly with something called sweep in a repo. Then we will also include wind feedback and couple it to the 2 modes of accretion and feedback. And I just want to highlight that tomorrow my colleague from Galspec, Marion Farsi, will have a talk about winds as well. And then in the far future, we will also like to implement this accretion model in a cosmological context by performing some zoom-in simulations at high redshift. And now I can take some questions if you have it. Thank you.
Really phenomenal work. So when you talk about the viscous time scale, you have to assume some value for the accretion disk viscosity alpha, right?
Yeah.
I think this varies widely in the literature by like several orders of magnitude. So have you looked at what choices do you make, and how sensitive are your results to your choice of alpha, or is this self-regulating?
I have not looked into this at all, really. I've just assumed 0.1, but
okay.
Yeah, that's definitely something I would like to look into more. Yeah.
Any questions?
Thank you. It's really interesting. I wanted to ask something about on this slide. Am I understanding correctly that from the circularization radius, you assume that gas falls on the accretion disk on the free fall time? Or
no.
Okay,
So from the free fall time, that's basically from your resolution limit down to the circularization radius, and that's basically your radius of your accretion disk.
Okay, and in the idealized case, so the collapsing sphere, have you looked at how the results depend on resolution?
Resolution?
Yes.
Yes, I've done a short parameter survey, and so far, in terms of accretion radius and resolution, it seems to converge quite well. The tricky part is trying to pick a good softening length for your black hole, because you want it quite small, but that can also lead to some very close interactions. So that's the more tricky part there.
Just the last quick one, if I can. So I also think I missed how you calculate the circularization radius.
Yes, I have an extra slide for this. So this is basically how I do it. So at each type step, when there is accretion, you calculate your circularization radius for your infalling gas. And then you basically do a new mass-weighted average from what's already existing on your accretion disk.
Thank you.
Hello, I'm Junyoung Jun. I'm a grad student at UT Austin, and today I'll talk to you about observability of low-luminosity AGNs. To start with the motivation for the talk, it's because JWST has recently observed many new high redshift AGNs. This plot shows one example of such an AGN at redshift around 8 or so. It's very massive. And then to produce these AGNs, you need some extreme conditions or environments that allow for Eddington to spread into accretion or for the formation of direct class black holes. But most likely, these observations are biased towards brighter objects. So there probably exists lower luminosity AGNs at these high redshifts as well that are more common and that are does not exist in as high dense environments as this one might be. So we wanted to study these low luminosity AGNs and what under like what usual cosmological environments, how they evolve and grow. So for that, we use cosmological simulations. And this talk is based off of this published paper this year. As you can see, my other collaborators here. So our goal was to simulate the typical black hole growth in a cosmological environment at high redshift in the early universe. So for that, we use the Gizmo code, and we use the modified version of Gizmo used in previous works. The relevant modifications for this talk is that they include this new model for star formation feedback. So specifically, they include a star formation for the first stars are metal-free, the POP3 stars. And these POP3 stars provides the seeds for the first early seed black holes. Then we also include photoionization feedback, supernova feedback from these POP3 stars. And then these early stars also have a slightly more top-heavy IMF, initial mass function, so that we could produce more heavy, this slightly higher black hole seeds than the more local black holes that we might observe today. So it's more specifically what we do is that we run the cosmological simulation from early times. We run it until the first stars form, and then we stop simulation, post-process it to identify the dark matter halos, identify the most dark matter halo at the time, we place the black hole at the center. We test 3 different black hole masses, starting at 300, 210 to the 4. So 300 is like the typical POP3 stellar seed black hole. 10 to the 4 is like the upper limit, or maybe like a stellar cluster seed black hole. So we try to test some range of stellar seeds that are possible. And then we just evolve that simulation even more and see how the black hole grows in this environment, what kind of gas can accrete onto these black holes. And for the black hole growth, we use the common Bondi hole equation shown here. Then we also include the thermal feedback from black holes, which are based on their accretion rates. But as we'll see in the next slide, that effect is not very large. That's because we see that the black holes generally have very low accretion rates and do not grow at high redshifts. So the top plots show the mass accretion rate, the bottom plots show the black hole mass growth. So the blue or black line in the slides show that what the output from the simulation, what's actually seen. And the red line shows the maximum, the Eddington accretion rates. So all the mass accretion rates for black seeds are some magnitudes below the Eddington accretion rate. Therefore, because the Eddington accretion rate is exponential, our black hole simulation mass growths are very linear and not growing. You can see this more clearly here. The left plot shows the black hole mass ratio to the initial mass. And then you see that our black holes don't even generally grow to twice their masses throughout cosmic history. And then we see the Eddington ratio at the right. And generally, we see that on average, in all cases, it's still around 1% Eddington ratio. So they grow around some magnitudes below what's maximally possible at these times. We compare our results to different observations here. So the 2 lines at the top shows the halo masses. The top line shows the total halo virial mass, and the bottom yellow line shows the stellar mass. We said our halos have a significant stellar mass component. We compare to the blue and the yellow boxes. Those are the observations from the JWST SEER survey. We see that the halo we simulate is much lower in mass compared to the SEER survey. The dashed lines at the bottom show our black hole masses that are very not growing. We compare them to JWST various JWST observations in the blue. The star shows the Larsen et al. Source showed early in the plot. The black hole mass is in the black, and its stellar mass is the yellow star. We also show the black hole mass and the stellar mass of GNG11. And in all cases, our simulated halo and black holes are lower in mass than the observations, which was to our goal, as we wanted to simulate the less bright, lower mass objects that are probably more common in the early universe. And we see that compared to them, our stellar seed black holes are much lower in mass and probably are not what produce these high redshift AGNs that have been observed so far. We also compare our black hole masses from the local M sigma relation. We do see that our masses deviate from that, but that might not be too significant as the M sigma relation is from a population of black holes, or in this case, we only test 3 cases and not much more. The reason for such slow growth, we believe, is partially from stellar feedback. So we show the gas temperature on the black hole and inside the halo in these plots. We see that generally the temperature is high from the photoionization and supernova feedback that goes around because from the stellar formation. We can see in the right, we show the stellar mass density, and we see that around the black hole near the halo center, there's again a lot of stellar mass that contributes to this high feedback, and the heated gas from the stellar feedback cannot accrete efficiently onto the black hole under the Bondi hole accretion subgrid model. And we show the gas temperature phase plots here at redshift 15 around when the first stars form around when the first enters the black hole, and around redshift of 5.6 when the simulation ends. Then we see that the 10 to the 4 gas, which corresponds to the gas temperature that was heated by photoionization feedback, exists in both at early times and late times, so that the heated gas exists from the start, and that because of that, throughout the whole time that we grow the black holes, they cannot grow. You can see I have some movies of the evolution of the halo here. You see the gas is inflowing inside the halo, but then that gas is heated that cannot efficiently accrete into the black hole. The phase plot also shows this gas flowing inside the halo. There's some cold gas that flows in, but then eventually is heated through stellar feedback, and there's the accretion onto the black hole is not significant and then there's low growth. Another effect we see for this low growth is this black hole wandering effect. So because we simulate lower mass halos and lower mass black hole seeds, the gravitational potential of these system is generally low, and then these low mass seeds cannot sink effectively into the dense central region of the halo. So we see here that the black hole seed is off the central gas region. And because of that, even if the cold gas is available to accrete, the black hole doesn't reside in that part, then the accretion rate cannot be maintained at a high rate. So on to observability, we used to test the observability of these black holes. We calculated the luminosity from these black holes through a multicolor disk model from previous work, which depends on the mass and the accretion rate. The left plot just shows a plot of that formula shown on the top right. And then which depends on the mass and the accretion rate on the y-axis and the y-axis. We plot some lines to make sure we're more clear. The 0.1, the 1% Eddington accretion rate shown in our simulations and the Eddington accretion rate. We also plot the Larsen et al. AGN has been observed for a sanity check. So the black line, the left plot shows the sensitivity. So what's to the right of the black line will be able to be observed, and what's on the left will not be. So the Larsen et al. AGN has been thought to be observed around Eddington, and it has been observed. So it is to the right of the black line, and it's also observable according to our model, so that agrees with observations. But our 1% Eddington line needs to have very high masses to be observed, and just from this plot alone, we can see that it probably won't be able to be observed with the JWST. That's what we see here. So we plot the flux across redshift at the F200 W filter at 2 microns. This red line on the top shows the filter limit. The solid lines at the bottom show the fluxes from black holes. So generally, our fluxes are much lower in magnitude at the filter limit and can't be observed. For comparison, we also show the Eddington fluxes. So the fluxes, these are seed black holes that would have produced if they had accreted at the Eddington rate. In those extreme cases, of course, the black holes grow fast enough to be observed at a high redshift as some of the observed sources have been. And then we show our black hole masses just to show how these low growths should produce low fluxes. We also include the analytical model for direct class black holes. again, for these extreme cases, these black holes are able to be observed. So it seems like we need some extreme conditions only to be able to observe these, and these more common cases at high redshift won't be never be able to be observed. So maybe under extreme case that these low C can be observed through gravitational lensing. So there have been extremely lensed point sources observed with JWST, like the point star Arundel. And because AGNs also act or behave like point sources at high redshift, we wanted to see if that extreme magnification could make these low luminosity AGNs observable, which they seem to by these lens fluxes. So these dotted and dashed lines at the top, I just multiply the flux values by the extreme lensing magnification values, and they do reach observability at extremely high redshifts. But again, like this magnification requires highly specific geometries for these extreme lenses to occur. And then while like galaxies host millions of stars, there's probably only just one central AGN. So this may be very unlikely to happen. So again, this is another extreme situation that makes these things observable. To conclude, we show that typical low mass black hole AGNs at central galaxies at high redshift aren't easily observable. And then we still haven't made other considerations, like these AGNs are resort in galaxies, and then we also have stellar luminosity that will maybe possibly overtake them. These AGNs may be obscured at high redshift. So the probability of observing them may be even lower than what we find in this work. For future work, then we will also work to see what environments that allow for these high redshift Eddington accretion AGNs that are observable. Thank you. I'll take any questions now.
Thanks, this is really interesting. So if I followed properly, you used Bondi-Hoyle accretion and you did not include feedback from the black hole itself. So is that correct?
There was thermal feedback, but that was based on the accretion rate. So with the low accretion rates, it was very insignificant.
Okay, so you don't have strong feedback from the black hole. So my thought is that both of those will actually, both of those are sort of optimistic, right? Like, so I think that if you used maybe a more physical accretion recipe and you included stronger feedback, then your black holes would grow even less. So what's going on?
Yeah, I guess that'll be the part of future work, because we do see the massive IGNs. Then there will be some other, because these are the general, like, more common regions of the universe. The cosmical box we simulated is a typical region, but maybe those more massive agents reside in more overdense regions where there are higher gas density, so that could be the feedback, there'll be a lot more cold gas, or maybe less stars, so that that feedback effect isn't as strong.
So maybe you didn't simulate quite the right environment for that.
Yes,
those particular
possibly.
objects. Okay.
This, I think it was only like 4 megaparticle box as well.
Other questions? Yes.
So just very quickly, you said that the black holes are not on the M sigma relation. You actually mean M sigma, so you calculated the velocity dispersion
The M sigma relation, I got that from like I estimate that from the halo mass, because I will use a relation between the halo mass and the velocity dispersion, and then use the velocity dispersion to get the black hole mass from the M sigma relation. So it's basically a two-step process.
So you didn't actually calculate the velocity dispersion of the stars?
No,
in the
not directly.
protogalaxies?
No.
Okay, thank you.
Okay, thank you. Next up, we have Jake Bennett.
Thank you very much. Yeah, sticking with the high redshift universe, but with much larger things, which came from smaller things. So that is still following on from the previous talk. Thank you to the organizers for having me. And yeah, so we're talking about high redshift quasars. Now, no. Good start. this is the plot on the left here is looking at is from the highest redshift to date. I think that's still true. Detected black hole, which is at redshift 10.6 in GNZ11, which was mentioned earlier. And the tracks you can see here, for example, the blue line on this plot is what the growth paths will follow if it was accreting at the Eddington rate consistently. However, actually accreting at the Eddington rate consistently is easier said than done because of feedback from the black hole on the surrounding gas and on the host galaxy. And as we kind of talked about a little bit before, seeding times and masses are very unconstrained. We don't really know where the black holes originally start from, whether it's from the stellar mass seeds as we were talking about, or higher mass direct collapse black holes of up to 10 to the 5, maybe 10 to the 6 solar masses at a push. And so to kind of give us more information about this, the motivation behind my project was to look at other indicators of the growth history of the black hole. So not just kind of observing the black hole itself, although that's a big part of what we'll talk about, given them in the accretion section, but actually what other signatures there are we can look for. And to do this, I've been using a cosmological zoom simulation and using the Fable model, which was kind of developed from the original Lustris model, but with a better prescription of AGN feedback. So it kind of much better matches low redshift galaxy groups and clusters. And so I'm using this halo that is about 7 times 10 to the 12 solar masses of redshift 6. So this is a big thing. This is growing. This is most likely the sources of these high redshift quasars. And I haven't really got time to go through all of the details of the two models are here, but the fiducial Fable model on the left and this what I call reference model on the right is when I make some changes to encourage earlier black hole growth. The summary here is basically we seed these large black holes a bit earlier, so you gain a couple of 100 million years. The maximum allowed accretion rate is twice Eddington rather than capped at the Eddington rate, which is not too dramatic a change, and it doesn't stay constantly out there, as you'll see. And also the quasar efficiency. So this is the amount of energy that is then put in the surroundings per unit mass accreted, we lower to. So the actual individual feedback episodes are a bit weaker, but as we'll see, that does not mean they have less impact. And so this plot is therefore showing the growth of these halos. So the dots we can see at the top left particularly are these high redshift quasar inferred masses from usually magnesium-2, but often H-beta nowadays, the GWST line widths. And the fiducial Fable model in pink here at the bottom, it significantly underpredicts some of these largest halos, particularly the ones at around redshift 7.5 or above, and the largest at low redshift, which has a little box around it. Redshift 6 is not low redshift. That has a little box around it is about 10 to the 10 solar masses at redshift 6.3. But what you can see is that the Fable model can reproduce in this bottom point here is from GNZ11, and this other point is the Larson et al. Detection that was in the previous talk. That can reproduce that reasonably well. You accrete roughly at Eddington. The average is below Eddington, but there is an Eddington cap on this. When you seed earlier and allow things to grow faster, you can grow earlier, and you can kind of be consistent with these largest and highest redshift black holes that we have in the known universe. So that's kind of the point, is that there is enough gas available to grow ridiculously large black holes if you can get it into the black hole, but maintaining very high accretion rate is difficult because of feedback. And kind of looking at the kind of gas content that we have here, these are dust masses, or estimated dust masses of the central galaxy. As you can see with the no AGN run, this kind of stays fairly constant. And this point with the square around it is the kind of the galaxy we were kind of closest to in terms of black hole mass. But the dust masses for even the Fable run and the run without AGN are much higher than this one from JR100 to 802. But with the reference run, we're close to this value. We are blowing out more gas and we are heating things up much more effectively because of this earlier feedback. You can see it kicks in a lot earlier. Now, this is kind of worth showing. So these averages here are showing the accretion rate over time. And so this is the Eddington fraction in the top and the bolometric luminosity in the bottom. So this is for the Fable run. So it is capped at the Eddington rate. But a lot of the time, particularly when feedback starts kicking in, you see that a lot of the time it's not at Eddington. And if you look at the actual bolometric luminosity that turns into, if you're capped at the Eddington rate, you're nowhere near a lot of the bright quasars that we see at high redshift. If we go to the reference run, we can actually see we get periods of averages slightly above the Eddington rate, with a lot of variation over time. And then as feedback kicks in, this really drops to sub-Eddington rates. But we kind of get luminosity is much closer to the observed values. But despite how bright these are, detecting them is not necessarily the easiest. So this is looking at the in 10,000 sight lines surrounding the black hole particle. This is the hydrogen column densities in the Fable and reference run. So if you look at a run without AGN, so these open pink squares, they basically hover around being Compton thick in all sight lines throughout the whole time. You've got not much chance of seeing this, even if it's at 10 to the 48 ergs per second, if you haven't had feedback to clear some sight lines out. In the Fable run, you see that happens to some degree. You broaden this distribution of column densities along different sight lines, and the reference run is a bit more extreme, and you really create a lot more sight lines where you can actually see this quasar. And if you look at how that how it looks visually, you see with a no AGN run, everything's there's a high column densities everywhere. You're not going to get many photons out of this in the rest frame UV. This is in Fable, you still have a kind of central disk type vibe, and you clip some spaces that are more clearer. In the reference run, this, because you have earlier feedback, this gets you a bit further in the right direction. And how this translates into the observation probabilities here. So this was then looking at UV extinction. Basically, for the various surveys that are upcoming, Euclid, Roman, the chance of observing the quasar in the Fable run here is about 30 to 40%, roughly, in terms of the number of sight lines that would be observable with these surveys. To actually increase this fraction and have this earlier feedback, then you can get this fraction up to just over 50%. This thing is shining at like 10 to the 48 ergs per second, but there's so much gas is having to be piled onto this galaxy to grow these black holes to such large masses that seeing them, it will be quite difficult. And getting around those two things, I'm not sure what the best answer is at this point. But then looking at what this does to some observations of the halo, so this was kind of the feedback parts, which is tomorrow, I know, but this is kind of assuming Bremsstrahlung approximation. This is at the simulation resolution, looking at what the X-ray halos would look like. And you kind of see in that we're wrong with that AGN, you have a very hot, dense core that's very bright in X-rays. In the Fable run, you start to blow some gas out of the center. But there's not a great deal of difference between this, despite this hosting the middle center panel hosting a 10 to the 9 solar mass black hole. On the right, you redistribute gas quite a lot because of this, particularly early feedback helps in this case with the potential wells a bit shallower too. But then actually looking at what you might be able to observe with this, Athena's probably not good enough to do. So I would say all of these X-ray predictions that I'm showing here are, as if you assume you can perfectly remove the quasar, which the PSF of these instruments is this dot dash line surrounding the images. This is just the X-ray emission from the hot gas of the halo itself. So in Athena, it would be very difficult to separate the two of them. There's a proposed probe called Axis, which you might be able to start separating the PSF of the quasar itself from the surrounding galaxy. In the cases with no AGN feedback or kind of intermediate AGN feedback, you might start to struggle when you have kind of strong early feedback because you're blowing out a lot of this gas, lowering central densities, and therefore lowering AGN brightnesses. And in an ideal world, someone will pay for links and build links, because that will be really quite cool. And even in the case of the reference run, where you're blowing out a lot of this central gas, you'll be able to detect photons from the halo itself outside of the PSF of the instrument, if that is the PSF that actually comes out in the end. So this would be a real game changer in looking at the actual, the hot CGM of a high redshift quasar. But actually, worth saying that obviously this is perfectly removing the quasar. If you actually have X-ray observations, then you can get around part of this obscuration problem as well. And there are various runs. There are various other probes like the line emission mapper probe, which has very high spectral resolution, which could give you a lot of information about the quasar itself too. I will kind of just come to my conclusions now, but in saying that if you have kind of plausible, reasonable changes to existing models, you can make the most extreme objects, most extreme black holes detected in the early universe if you're in a sufficiently large halo, is worth saying, that has enough gas coming in to be able to get into the black hole. But because of all that gas coming in, you might not be able to detect it in the rest frame UV at least, which is what most of the surveys are done in, because of obscuration, because you need a lot of material to grow. A lot of material blocks the photons. But there are potentially other cool signatures that we could start to use in the future to try and look for evidence of feedback and the past feedback, other than just being able to observe it in the first place. And particularly the potential of X-rays in the next decade or two, and potentially with the SZ effect, you can get the angular resolution that you need to detect the differences in the SC effect with ALMA, not probably within a reasonable time frame currently, but these are kind of potentially quite good ways of probing the growth history because of looking at when this feedback kicked in earlier on. Thank you very much.
Thank you, super nice results. I was wondering, when you're modifying your parameter for the scaling accretion, etc., to make those black holes grow, you showed the mass of the dust, but you didn't comment on the black hole stellar mass or black hole gas mass and how this evolved this time.
If I go back to the actual growth plot, so here the bottom, I didn't have time to talk about this, but the bottom of this blue region here is the redshift 0 median stellar mass to black hole mass relation for one of the runs, if I just convert the stellar mass to the black hole mass. And so the Fable run lies reasonably around that by redshift 6. The red line, the bottom of this red region here, is the kind of record inferred stellar mass to black hole mass relation of about 15%, I believe, which we're still underneath that even with the reference run. It is overmassive compared to the redshift 0 relation. Would you expect the redshift 0 relation to still exist at redshift 10? Don't know, but that's kind of, yeah, it's reasonable what we've found potentially, but the constraints aren't there to say whether we're not there yet to say whether we're too high or too low at that particular time.
Thank you so much. Great talk. So I wanted to know if you can comment on the profiles of these halos at early redshift. Would you expect them to have some cusp or core type distribution?
In terms of the dark matter? Or
yes, the dark matter.
I haven't actually looked at the dark matter, honestly. What we notice even in the gas is that it depends how early a time you're talking as well, because what we notice is that even when you're in the reference run where you're growing things much earlier, if you look at something like redshift 10, redshift 11, the actual amount of feedback that you can't really tell that there is an AGN there that's feedbacking on the surroundings. Now that's partly potentially due to the specific model that's used for. It doesn't have a great deal of impact on the gas distribution, so therefore I wouldn't expect it to have much effect on the dark matter distribution either. In the Fable run, kind of the reference run kind of kicks in and starts to redistribute gas by kind of redshift 10 to 8, whereas the Fable run doesn't really do that until kind of redshift 7-ish. So there might be some differences at that point, but I haven't specifically looked at the dark matter profiles in this case.